So this is where we left off, chemical formulas. So how do we represent compounds that have polyatomic ions? So we've got these polyatomic ions. These are the sulfates and the phosphates and things like that. These polyatomic ions are groups of atoms that act as a unit. So it's a little bit like buying things at Costco, okay? If you go to Costco and you want to buy a Wii or an Xbox, you don't just get the game system. It's bundled packed with some stuff, right? You get an extra controller and you get 3 games or something. It's all shrink wrapped, right? And you can't just buy part of it. So the polyatomic ions are like that. It's a package deal. You have to have the whole thing. So when we have more than one of those, we have to indicate that in a way that's not confusing. And so we use parentheses. We're going to use parentheses around those when we have more than one of the polyatomic ion. So they're called polyatomic ions. Poly meaning many, atom meaning atom. So many atom ions. So let's look at this. So here's an example. Here's the formula right in here. Here we have Mg, and in parentheses, we have NO3. The parentheses are like the shrink wrap. They're holding this thing together. NO3 acts as a unit. And the subscript on the outside tells us how many of those packages we have. What color do I have going on here? Let's go with black, perhaps. Because if we wrote it without the parentheses, MgNO3, 2, that looks like 32 oxygens. That's confusing. Okay, so we need the parentheses when we have more than one. If we had a different compound with only one of those, say sodium nitrate, then we don't need to put the parentheses when there's only one. So just like we don't write the number 1, we're not going to put the parentheses with a number 1 that we're not going to write. So this example is showing us, here we've got the symbol for the NO3 minus group, the nitrate group. This subscript 2 tells us that there are 2 of those groups. So this is a little bit like math. You know, if you have 2 times A plus B, that 2 multiplies everything inside, right? And so we could say that this 2 distributes across the nitrogen and the oxygen. And out here we have magnesium. So what they're asking us to do here is determine the number of each type of atom in this formula. And this is an important thing to be able to do. So how would we answer this? Well, I'll just kind of scribble it up here. So how many magnesium atoms are indicated in that formula? 1. There's no subscript after magnesium. That implies that there's 1 of those. Now, another element that's in there is nitrogen. How many nitrogen atoms are in there? 2. Because this 2 means there are 2 of these package deals. Each package has 1 nitrogen. We've got 2 packages. So we have 2 nitrogen atoms. And then the other element present is oxygen. And how many oxygens? 6. Because each package has 3 oxygens, 2 packages means we have 6 oxygens. It's a very important concept that sometimes I always have 1 or 2 students that just kind of slip through the cracks on that one. So don't be one of those people. So another example. Determine the number of each type of atom in the following formulas. So we need to be able to do this before we can do things that are coming. So to answer a question like this, just list off the elements that are present. So we've got potassium, we've got sulfur, and we've got oxygen. How many potassium atoms in the formula? 2. How many sulfur atoms? How many oxygen atoms? 4. Right? Did you say 4? It was all mumbled together. And in this one, we've got aluminum and sulfur and oxygen. Again, with the sulfate, that's kind of boring. How many aluminum atoms? 2. How many sulfur atoms? 3. How many oxygens? 12. Sometimes the number of atoms of a particular element gets pretty high. It could be 35 or something. Don't say, well, it can't be that big. We don't use numbers that are that large. Well, yeah, sometimes we do. Sometimes there's like 150 carbon atoms in one molecule. That's not crazy. Any questions? There are different types of formulas. So, an empirical formula. The word empirical, yeah, okay. I always do that. Sorry, I'm mumbling to myself. Empirical means by experiment. Empirical formula gives us relative numbers of atoms of each element in a compound. That's going to give us the lowest ratio. It's not always going to tell us how many atoms are actually in a molecule. It's just the lowest ratio. The molecular formula is the formula of a molecule. So that gives us the actual number of atoms of each element in a molecule. Sometimes the empirical formula and the molecular formula are the same, and sometimes they are not. It's a little bit like fractions. So the actual amounts might be in a ratio of 4 to 2, but that is a relationship of 2 to 1. And so an empirical formula is like the reduced fraction, and the molecular formula is the actual number, which may or may not be in its lowest state. And then the structural formula. Structural formula shows us the structure, shows us how the different atoms are connected to each other. And at this point, we're not as concerned about that. We're learning about the empirical and molecular formulas. We also have different types of models. A model is a three-dimensional representation. So a molecular model is a three-dimensional representation of a molecule, just like a model car is a little plastic replica of a real car, right? So there's different ways we can represent molecules. One is the ball and stick model, where we have the atoms as balls and the chemical bonds are sticks, and we put them together and it's like science Tinker Toys or something. Then we have space-filling models. Those more closely approximate how an atom, a molecule actually looks. And so a lot of the drawings that we see in the book and in the PowerPoint slides are space-filling models. In the ball and stick model, we tend to use these colors to represent these different elements, and you don't have to memorize that. That was just a pretty picture. So let's compare some different formulas and models for a particular compound. This compound is methane. That's natural gas, and its molecular formula is CH4. So the molecular formula CH4 tells us that we have one carbon atom and 4 hydrogen atoms in a molecule. So here's the molecular formula. The structural formula shows us how they're connected. Shows us that all the hydrogen atoms are individually bonded to the carbon atom. So if you imagine these as balls and sticks, which this is, I find this the easiest way to visualize atoms. You know, in chemistry land, it's like I decided I'm going to call it chemistry land. It's like Disneyland, right? It's chemistry land. It's a fun place. Maybe not the happiest place on earth, but it can be fun. Anyway, in chemistry land, I see atoms as being a lot like marbles or billiard balls or something, but you can stick them together with sticks. And so this shows us, written conveniently on paper using letters, a representation of this ball and stick model. There are other ways, you know, imaginatively, that you could combine 4 white balls and a black ball, right? You could say, well, why isn't the black ball at one end, and we'll just make a chain of all the little white balls, and it's like a mother duck and her ducklings, and they're following behind her, and it's all in a row. But that's not how it is. And so this shows us how it is. And at this point, you would not be expected to predict this. This is an example of a space-filling model. Because is a molecule actually atoms that are just stuck together with little tinker toy rods? No. It more approximates this space-filling model. But these are hard to draw and hard to build, and so we let the computer generate those for the most part. Any questions? Yes.